So finding roots of general cubic polynomials is always a little bit more work than it's worth. But that being said, I recently found this take on finding these roots that's a little bit nicer than most takes. And it's from an article from the National Math magazine from 1935. Okay, so let's see how it goes. So let's start with an arbitrary cubic. So maybe we'll say it's of the form w cubed plus 3a times w squared plus b times w plus c equals 0. And you might say, well, why am I using w as my variable? It's because I'm going to perform a couple of changes of variables. And, well, we got to start with something. And you might also say, well, why did I scale this coefficient right here by 3? And that's to make things work out a little bit more nicely. But you could just absorb that into the coefficient of w squared if you would like. Okay, so we're going to start with a substitution. And this substitution is somewhat normal for maybe the first step of solving sort of cubic polynomials. So we haven't changed from the norm just yet. We'll set w equal to z minus a. So let's see what that does for us. So here we'll have a z minus a cubed, and then here this will be plus 3a times z minus a squared plus b times z minus a, and then plus c equals 0. Okay, so let's do a simplification on this and see what we get. So maybe I'll do a little bit of color coding here. Okay, so expanding this out using a binomial formula, making sure to put this in green parentheses, we have z cubed, and then next we'll have minus 3a times z squared, and then plus 3a squared times z, and then minus a cubed. So like I said, that's from the binomial theorem. And then let's see, I'll maybe go ahead and underline this in this nice magenta color, and then we'll put that in a magenta parentheses. So that'll give us 3az squared, and then we'll have minus 6a squared z, and then finally, let's see, it'll be plus 3a squared, or sorry, that should be 3a cubed. And again, that's from multiplying all of that bit out. And then let's see, we'll have purple parentheses for this little bit. So that'll be bz minus a times b. And then finally, we have this plus c term. So now let's see what sort of simplification occurs. So we've got a 3az squared term, it's attached to a minus sign. 3az squared term is attached to a plus sign. So that means all of this cancels with all of this. But in fact, that's the only z squared term. After that, there's only linear terms, in other words, z terms. So we've got one right there, and we have one right there, and we have one right there, and there are constant terms. So this transforms this into something of the form z cubed plus something times z plus something else. Okay, nice. So that means that we should instead consider this so-called reduced cubic. And so let's give these things some sort of names. And so let's consider the cubic, which is z cubed plus 3pz plus q equals 0. Where the p and the q are really whatever it takes to fill in these boxes after combining the terms over here. We'll see that in the end it doesn't really matter. Well, I mean, obviously it matters, but we won't have to write it down explicitly. Okay, so next up we're going to make another change of variables. So let's do that. So let's take every z here and replace it with x over y. So that's going to give me x cubed over y cubed, and then plus 3 times p times x over y plus q equals 0. And then from there, we're going to clear our denominators. So in order to clear our denominators, we need to multiply by y cubed. So let's see, multiplying by y cubed will give me x cubed, and then plus 3 times p times x times y squared plus q times y cubed equals 0. So that's my new equation. And now I'm going to call that two-variable polynomial a function f. So let's do that here. So we'll set f of xy equal to, well, like I said, that cubic polynomial in two variables, so x cubed plus 3pxy squared plus q y cubed equals 0. Or maybe I don't need to put equals 0 there. This kind of manipulation changes my cubic polynomial to a homogeneous cubic polynomial. Notice every term here has degree 3. And this is common when you're pushing from, for instance, the complex plane to the complex projective plane, but that's kind of another story. So next up, we're going to consider something called the Hessian of this function. And so maybe I'll call that h, and what it is, it's the determinant of the matrix built out of all of the second derivatives. So here we've got the pure second derivatives on the diagonal. So that'll be the second derivative with respect to x, the second derivative with respect to y, and on the off diagonal, we'll have the second derivative, one with respect to x and one with respect to y, where here I'm like using partial derivatives. Okay, so what does that give me here? So that's going to give me the determinant of, so the second partial with respect to x will be 6 times x. I think that's pretty clear. And then the second partial with respect to y, what'll that be? Well, that'll be 6 times p times x plus 6 times q times y. And then the mixed partials you can calculate as well, and those are both going to give you 6 times p times y. Okay, great. And I guess we should mention here that the reason these look the same instead of one being fyx is because since we're working with a polynomial, well, we know the order of the partial differentiation doesn't matter. In fact, most of the time it doesn't matter. There's a nice theorem that says when we can switch the order of partial differentiation, if you'd like to look that up. Okay, so now taking this determinant, we'll get 36 times, well, let's see, what will it be? E times x squared plus q times xy minus p squared times y squared. Okay, so that's just using the standard determinant formula, keeping in mind that I've got a factor of 6 there everywhere. And since I've got a factor of 6 there everywhere, I can factor that 36 out. Now our goal is to look at when h equals 0, when this Hessian equals 0. But notice this Hessian is equal to 0 if and only if the following object is equal to 0. And that object will be gained by taking this term right here and dividing it by y squared. So we'll have p times x over y squared plus q times x over y minus p squared equals 0. But now maybe performing our substitution in reverse, our z equals xy in reverse, we have a new maybe one variable polynomial that looks like this. We have z squared plus q over p times z minus p equals 0, where I also divided by p there. But the fact that we divided by p means, well, that this coefficient of z was not equal to 0. But let's look at this. If this coefficient of z was equal to 0, then it would be very, very easy to find the roots of the corresponding cubic, so we might as well not worry about that. Okay, so let's maybe reiterate what we've just done. So we've looked at a homogenized version of our reduced cubic, and then we found the Hessian of that. And then after finding the Hessian, we looked at the zeros of the Hessian and made that correspond back to a quadratic polynomial. Okay, so now let's see what we can do with that quadratic polynomial. Starting with our arbitrary cubic, we made a change of variables, well, a linear change of variables that turned it into a reversed cubic. And then passing through something called the Hessian, we got this quadratic polynomial. And now let's take the roots of this quadratic polynomial. So let's say R1 and R2 are the roots of, well, this quadratic polynomial. So I'll maybe just put an arrow up here. So what does that mean? Well, that means, in fact, we can make this factorization of z squared plus q over p times z minus p must factor as z minus r1 times z minus r2. But now we can multiply that out and we get z squared minus r1 plus r2 times z plus r1 times r2. So here we're using like Vieta's formula to write p and q in terms of r1 and r2. Okay, so let's see what we've got here. So here we've got a coefficient of z, which is q over p. And here we've got a coefficient of z, which is minus r1 plus r2. Whereas here we have a coefficient of z, which is minus p. And here we have a coefficient of z, which is r1 times r2. So putting this together, we've got the following equations. So we have p equals minus r1 times r2. And then we have q over p is equal to minus r1 plus r2. So we can easily solve for q here, maybe putting these things together, and we'll see that q is in fact r1 times r2 times r1 plus r2. Okay, nice. So there we have it. We've got this nice expression of p and q in terms of the roots of this corresponding quadratic equation. And now let's substitute that into our reduced cubic. We're calling that our reduced cubic is, well, it's this equation right here. So that's going to look something like this. So we'll have z cubed minus 3 times r1 times r2z, and then plus r1 times r2 times r1 plus r2 equals 0. So that's our reduced cubic, where the coefficients have been written in terms of the roots of that corresponding quadratic polynomial. And now before we move on to a more general case, let's maybe look at the simplest case, which is the case when r1 is equal to r2. So what will that give us? Well, in this case, our cubic turns into the following equation. So we've got z cubed minus 3r squared z plus 2r cubed, where I should point out that here I'm setting r1 equal to r2 equal to r. Okay, so now our cubic equation is this. But now that's actually pretty easy to solve by so-called visual inspection. Notice if we set z equal to r, well, that ends up being a root of this cubic. We can see that. It'll be r cubed minus 3r cubed plus 2r cubed. So like I said, by visual inspection, we see that r is a root. And then after that, you can maybe use polynomial long division to divide z minus r out. And then that'll lead you to a full factorization of this, which is z minus r squared times z minus 2r. Sorry, that should be z plus 2r. And so that's how that factors, implying that we have roots that are r, and minus 2r. But then in terms of our original equation, we really have roots of w equals, let's see, it'll be r minus a. So r minus a, another r minus a, and then a minus 2r minus a. So those are the roots of our original cubic, our unreduced cubic. That being said, this case is not super interesting. Well, I guess it is interesting. But what we'd really like to look at is the case when r1 is not equal to r2. So let's do that. Okay, so starting again with our reduced cubic, but now we're looking at the case when the roots of this corresponding quadratic are not equal. Okay, so now we're going to do a nice change of variables. And so what will that change of variables be? Well, let's set u equal to x minus r1 times y. And then we'll set v equal to x minus r2 times y. And let's see what that gives us. So we can solve that for x and y, maybe just using like standard methods of solving systems of equations. And we'll end up with x equals R2u minus R1v over R2 minus R1, whereas y is equal to u minus v over R2 minus R1. Okay, great. So now we've got an expression for x and y in terms of u and v. But you might say, well, where are x and y's? Well, we haven't used them for a couple of steps, but let's recall that this reduced cubic had the following homogenized form. And so that form was something like this. It was x cubed minus 3r1r2 xy squared plus r1 times r2 r1 plus r2 times y cubed equals 0. So now what we'll do is take those values of x and y with our change of variables, and we'll plug them into this homogenized form of our reduced cubic. But what's that going to give us? Well, notice that everything here is cubic in xy, and x is a multiple of 1 over r2 minus r1, and so is y. So that means we should be able to factor out a 1 over r2 minus r1 all cubed from this. And then really now we can just work with the numerators. So that means for this x cubed term, we'll have r2u minus r1v all cubed. And then here we'll have minus 3r1r2. And then we'll have r2u minus r1v. So that'll be our x term. And then u minus v squared. That'll be our y squared term. And then finally, we'll have this plus r1, r2, r1 plus r2, and then u minus v all cubed. Okay, so we've got something like that. But at this stage, it's just a bunch of expansion and combination of all of this stuff. And in fact, it's not super interesting. So let's maybe skip most of that and just point out that that's going to turn into the following expression. So we'll have this 1 over r2 minus r1 quantity cubed. And then all of that on the inside simplifies to r2 times r2 minus r1 squared times u cubed, and minus r1 times r2 minus r1 squared times v cubed. And then we want to set that equal to 0 because, you know, that corresponds to this, which is our goal to find out when that's equal to 0, because that's corresponding to our reduced cubic being equal to 0. Okay, nice. But now let's see what we can do. We can cancel this r2 minus r1 squared and this r2 minus r1 squared with 2 out of 3 of those exponents. And then note that this thing out front is never equal to 0. So that means this is equivalent to having r2u cubed minus r1v cubed equals 0. But from here, we can solve for u in terms of v. And that'll look something like this. So we'll have u is equal to the cube root of, let's see what it'll be, r1 over r2 times v. But that's only one of the parts of the cube root. There are others as well, and those are u equals so-called omega times the cube root of r1 over r2 times v. And then u equals omega squared times that cube root of r1 over r2 times v. And you might say, well, what is omega? Well, it's e to the 2 pi I over 3. In other words, it's a primitive third root of unity. That being said, just for simplicity, we're going to focus on this one right here that does not have the multiplier of that primitive third root of unity. We'll maybe like add it back in at the end. Okay, so now let's take this value of u and see what we can find out about x and y and thus z. Okay, so this is where we just ended up. After our substitution, we found u in terms of v. But notice knowing u in terms of v means that we in fact know x in terms of y, because u and v can be written in terms of x and y. So notice in fact we know that x minus r1y is equal to, well, the cube root of r1 over r2 times x minus r2y. Okay, great. But what we really want is z. And we can grab z fairly easily by multiplying this by 1 over y, because remember that z was equal to x over y. So let's see what that leaves us with. So that's going to leave us with x over y, which is, like I said, z, minus r1 equals the cube root of r1 over r2 times z minus r2. And so now for simplification purposes, I'm going to clear the denominator here, and I can do that by multiplying by the cube root of r2. So that's going to leave me with the cube root of r2 times z minus the cube root of r1 cubed times r2, just multiplying that r1 inside of the cube root. And so that's going to be equal to the cube root of r1 times z minus the cube root of r1 times r2 squared, for kind of the same reason. And now let's see, we can move everything with a z to one side of the equation. That'll give us something like this. So we'll have the cube root of r2 minus the cube root of r1 all times z is equal to the cube root of r1 cubed times r2 minus the cube root of r1 times r2 cubed. And then let's see if we can factor some stuff out of that right-hand side. And in fact, we can. There's a greatest common factor of what looks to be the cube root of r1 times r2. So factoring that out, I'm also going to factor out a minus sign, and we'll see why later. So the cube root of r1 times r2, and then because we're factoring out that minus sign, we'll be left with the cube root of r2 quantity squared minus the cube root of r1 quantity squared. Okay, good. But let's look at this. This is in fact a difference of squares. It's cube root of r2 squared minus cube root of r1 squared. So that means we can factor it out. That'll factor as the cube root of r1 squared, the cube root of r1 minus the cube root of r2, and then the cube root of r1 plus the cube root of r2. Okay, then we can divide by this cube root of r2 minus cube root of r1, and that'll cancel down. And that'll leave us with z equals, well, then we can multiply this back through. We'll have minus the cube root of r1 squared times r2 minus the cube root of r1 times r2 squared. So there's a root for our reduced cubic. But then if we want to write down a root for maybe like our original cubic, what will we have? Well, we'll have to subtract off a. So that means here a value of w, which will be a root of our original cubic, will be minus a minus the cube root of r1 squared times r2 minus the cube root of r1 times r2 squared. There we have it. We've got a nice formula for a root of our original cubic. Okay, so let's maybe summarize that and we'll do an example. So here's our summary. Our original big cubic can be reduced to a so-called reduced cubic. This quadratic polynomial was interesting. We found its roots, r1 and r2, and then we were able to write the roots of our original cubic in terms of those roots. So this is the one in the green box that we just talked about, and the other ones correspond to this right here. So we've got omega squared and omega sprinkled in, where omega is at e to the 2 pi I over 3. In other words, a primitive third root of unity. Okay, so now let's look at an example. So let's start here with w cubed plus 3w squared plus 9w minus 5. So let's do our reducing substitution first. And in this case, it'll be w equals z minus 1. So I won't work through all of the details on this. This is just a bunch of symbolic manipulation. But what you end up with is z cubed plus 6z minus 12 equals 0. And then from that, we can grab like our important quadratic polynomial, which we argued how to get that earlier, and that'll be this. So remember we called it h, and it'll be equal to z squared minus 6z minus 2. We want that to be equal to 0 Maybe I'll erase it being called h because that wasn't exactly h. That was like h up to multiplication by a constant. So now let's find roots of this quadratic polynomial, which we can do using the quadratic formula. So here we'll have r1 is equal to 3 plus the square root of 11, and r2 is equal to 3 minus the square root of 11. So again, that's just by the quadratic formula. So now putting this all together, we get a root of this polynomial can be written as follows. So it'll be -1. And then before we go any further, let's maybe note that r1 times r2 here is equal to 3 squared minus square root of 11 squared. In other words, the number -2. That'll be useful. So plugging it all into this over here, we'll have -1, and then these minus signs will change to pluses because of this minus here. We'll have plus the cube root of 6 plus the square root of 11, and then plus the cube root of 6 minus the square root of 11. Okay, so there we've got it. We've got a root for our cubic polynomial, and like I said before, the other roots can be gotten just by sprinkling these third roots of unity in here. So what do you think? Is this an easier approach to getting to the cubic formula? Maybe post in the comments, and that's a good place. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.